Okay. Z-score, before we get started, Z-score is a formula that you're going to be using, but you don't necessarily need to memorize because it is on our formula sheet. This is what the Algebra 2 formula sheet looks like. You have shapes that you're not going to use, don't know why they're there. You have the quadratic formula. We have everything from this unit is right in the middle. We have the Z-score formula right in the middle, and then the other two formulas we're going to learn on day 4 are right here. And then all of the rest of the bottom half is from Unit 9 that we're going to talk about a little bit later on. So this is your formula sheet that you guys will have available. The formula we're going to learn for Z-score today is something you do not need to memorize because it will be on the formula sheet. Okay? Alright. So what we're going to do today is talk about Z-score. So we're going to do a little bit of review. Oops. To start with. So I want you guys to have your calculator out. We're going to find the mean and standard deviation for that set of data. So go ahead and do that for me. Huh? Go ahead and find the mean and standard deviation. We are going to round to whole numbers. They should be pretty close to whole numbers anyway. We're going to round to a whole number just to make it easier for us. So 4. Well, when they have the little squiggle there. I'm just letting us do that here because if we use decimals, it's going to make the example problems we're going to do a little bit difficult. Right? So the mean is 4 and the standard deviation is 2. We're going to have them as whole numbers just to make the examples a little bit easier to work with. So on average, the dogs are what? 2 years younger or older. Yeah, so that's another way to understand the standard deviation. So if you know the standard deviation is 2, that means that they are on average 2 years younger or older than the mean. Okay? So what we're going to do is we're going to practice working with this guy right here, which is called a bell curve. We're going to be using bell curves to help us understand Z-score and probability once we move on to that next lesson. So to represent information, we use a graph called a bell curve or a normal distribution. Normal distribution. A normal distribution curve. Right. We call it a normal distribution because look at how the curve is kind of drawn. You have fewer points out here and more points as you get more towards the middle of the data set. So that's why it makes this kind of shape. They're assuming that the majority of the points are near the mean, and then as you go further out from the mean, there are fewer points. So that's why it creates that kind of curve. This curve is going to be perfectly symmetrical. Symmetrical. So that means one half of the graph on one side of the mean is going to be exactly the same as the other half on the other side of the mean. The line of symmetry right here, if you want to draw a little arrow, line of symmetry right there in the middle, that represents the, what do you think? The mean. It represents the mean. The line of symmetry, the line that goes right down the middle, that represents the mean value, the average. Each consecutive mark here along the bottom here, each of those little marks to the left and right of the line of symmetry represents standard deviations. Standard deviations. Okay, so you guys are going to be responsible for labeling these using your data. So if the mean goes in the middle, and I'm talking about the gray box up there, what number could I label the middle? 4. We know that the mean is 4, so whatever the mean is, that number goes right in the middle. Each one of these little notches here along the bottom represents a standard deviation. So if we know the standard deviation is 2, you're not going to write down 2. We know the standard deviation is 2, so if I go 1 standard deviation away from the mean, what would this value be? 6. If I go 2 standard deviations away, it would be 8, and then 10, right? If I go 1 standard deviation below the mean, I would have 2, and then 0, and then negative 2, right? So each one of these little notches represents 1 standard deviation. That standard deviation is going to be a number. So you're either going to add that on or subtract it, depending on which way you're going. You just add or subtract standard deviations to label, okay? I know. So sometimes the information is not going to be relevant. I know. But you can still label it. It's just not going to be used. So based on this information, I'm going to ask you guys a few questions. Right, we have the bell curve drawn. I'm going to ask you a few questions about the bell curve. How many standard deviations away from the mean would a dog that is 10 years old be? You go 1, 2, 3 standard deviations away to get to 10. You're counting notches. Whenever they ask you for standard deviations, you're counting the notches. So if they give you a data point like 10, you look for 10, how many notches is that away? 3. What about 4? How many standard deviations is 4? 0, because that is the mean. So it's 0 standard deviations away from the mean. What about 2? That would be, well, it would be -1. So when you guys are going left, it should be negative, right? When you guys are going right, it should be positive. So write a little note to remind yourself. You do have to indicate which direction you're going. Are you going above the mean or below the mean? If you're going right, so that's above, you would make it a positive number. If you're going left, you would make it a negative number. All right, what about 7?
1.5.
1.5. See how 7 is not an exact number, but we know it's exactly between 6 and 8? So you go 1 and then 0.5 standard deviations away. Okay? So that's how you guys can label and analyze a bell curve. Let me ask you some questions like that. Now the questions I was asking you when I said how many, right? This question, how many standard deviations away from the mean are you? That's the z-score. That's the definition of a z-score. So z-score is how many, I'm going to abbreviate, how many SD for standard deviations is a point away from the mean. How many standard deviations is a point away from the mean? That is the definition of a z-score. So instead of saying how many standard deviations away, I could say what is the z-score for a 10-year-old dog? They both mean the same thing. Okay? All right, a positive z-score means that the data value is what? It's positive. It's right of the mean. Right, I'm going to write right / above the mean. It's going to be on the right side of your bell curve, or thinking about it differently, you think it's above the mean. What if the z-score is negative? It's left or below the mean. Okay? So using the same bell curve, I'm going to have to scroll down, but you guys can still see the picture on your notes. I'm going to ask you the same kinds of questions with different wording. So instead of saying how many standard deviations, that language, I'm going to say what is the z-score for a dog that is 5.5 years old? 5.5. 0.75. Drew, how did you get that?
Well, 5 would be half of standard deviation.
Yeah. Exactly. So if I asked for 5, if I said just 5 years old, what would you say? 0.5. But then I added that half of the year, so you're doing half of the half, which is another 0.25. So to get 0.75, you do that kind of idea. Don't worry, we're going to have a formula that's going to help us do it in a second. But intuitively, you can look at the picture to see that same idea. Okay? What about if I asked for a 1-year-old dog? Negative 1.5. Because to get to 1, you would have to go past 2 a little bit more. So you have to go 1 standard deviation, then half of a standard deviation to get to 1. Alright? So you can use whole number increments or decimal increments when you guys are working with these things. So just make sure you're really, really careful. So looking at the picture can help you understand how the z-score works intuitively, but we do have a formula. So if they start giving you something like last 3 years and 2 months or something like that, you wouldn't be able to find that very easily with the picture, right? Because it's not an exact increment. So we have a formula. So when the data point in question is not exactly a standard deviation or something that you could find with an easy fraction, you have a formula. Okay? So for example, if I was asking a 7.4-year-old dog has a z-score of 1.7, right? I want to see if you guys can figure out what the formula would be. You may have seen it before. right? And it was very, very small, and I showed it to you guys, probably didn't see it. I want to see if you guys can figure it out on your own. So I'm telling you that the actual age is 7.4, and then I'm telling you that the z-score is 1.7. I want to see if you guys can figure out what the formula is. I'm messing around with some numbers. I want to see if you guys can figure it out. Alright, so the formula is going to have the data point in it. It's going to have the mean, which in our case was 4, by the way. And then it's also going to be talking about the standard deviation, which was 2. Alright, so I need you guys to see if you can do something with a 7.4, a 4, and a 2 to get to 1.7. You guys are going to experiment. All this page is talking about the same information from the very, very top. So the mean is 4, the standard deviation is 2, and the data point is 7.4. I want you guys to experiment. See if you could do something, multiply, add, divide, whatever. See if you can figure out how to get to 1.7. I'm going to give you guys a few minutes. See if you can figure it out. And if you think you got it, wave me over and I'll tell you if you're right or wrong.
Sure, it was early, man.
Come on.
We have one person already found it.
I thought it was
5 people right now.
Already done symbols.
I did.
There's no 6. There's no 6. You're only using those 3 numbers, 7.4, 4, and 2. You guys be experimenting, see if you can figure it out.
Come on, Jonathan. Even I got it. Oh, I saw it when you had the.
I was gonna say you're the closest.
You got it.
Okay, good. Justin?
Can I say?
Sure.
7.4.
Do I have to put like the X?
Well, you can do it in numbers first, then I'm gonna have you write it in symbols.
Minus 4.
Okay? And if I wanted to make that a symbol kind of formula where I could plug in anything, how would I write it?
X minus mu
Over.
over sigma.
Yes. This is your formula for the z-score. You're going to take the data point that they give you, you're going to subtract the mean, and then divide by the standard deviation. That's how you find the z-score. Okay? So now that you guys have the formula, I want you guys to try to find the z-score for all of these pieces of information. All of these numbers they give you, those are the x. Alright, the standard deviation and the mean are from the very top, the 4 and the 2. They're the same information we've been using all along. So I want you guys to find the z-score for all of those. Yep, we'll use 4 for the mean and 2 for the standard deviation. Be very careful entering it into your calculator. Does anybody have the z-score for a 3-year-old? No. What? Negative 0.5. What about a 2.6? Negative 0.7. Justin, I got you for the next one. 0.25. True.
Negative 1.60.
Yes. Alright, so that's how you guys find z-score. And again, the wording they may use for z-score is how many standard deviations away from the mean is blank. You have to remember that's the definition of z-score so you can understand it if they use that language. Okay? Now, just like we compared standard deviations, when we found standard deviations on day 1 and we compared like which one was most consistent, which one was least consistent, and we did that kind of thing, we're going to do the same thing for z-score. We're going to use z-score in a comparison kind of sense. So normal distributions are often represented using the mean and standard deviation. Standard deviation. In the following formula. So not only can they write it in a bell curve, they also write it in notation. It looks like this. I'll write it and then explain it. Yeah. X, squiggle, then capital N, parentheses, mu, comma, sigma, parentheses. So, capital lowercase. So what this means, and if you want to write it down in words, you can. What this means in words is that X, the data point, is approximately normal when the mean is this and the standard deviation is that. They're going to plug in numbers. Alright, so again, it says that the data is approximately normal when the mean is blank, whatever number they give you, and the standard deviation is blank, whatever number they give you. Okay, that's what that means in words. Okay, so they may give you a question that has just that. They don't have any like words or introduction. They'll just give you this, and they expect you to use that to move forward with the question. So really all that you guys need to extract from this is what the mean and standard deviation are. You guys have to remember that the mean is first and the standard deviation is the second. Okay, so that's what's important about that notation. So we're going to take this little word problem here. We're going to use the information in here. We're going to write down the formula that looks like this, but for each of them. We're going to label the pictures, and then we're going to answer some follow-up questions based on that. Okay? So it says the distribution of women's heights is approximately normal with a mean of 64.5 inches and a standard deviation of 2.5 inches. So we're going to stop there and draw a little line, change up our thinking. I'm going to take just that information and I'm going to write down the formula here. So the x squiggle n, x squiggle n does not change. That's the same for anything. What changes is what the mean and standard deviation are, and you get that straight from the word problem. So what was the mean? 64.5. So you'd write that down. I don't know why there's a dot there. And then comma, 2.5, close parentheses. Yeah, that's how we represent that information with the information from the diagram, or the word problem. Now we're going to do it again. It says the distribution of men's heights is approximately normal with a mean of 69 inches and a standard deviation of 2.5. So how would I write that? X squiggle n. You have your mean and standard deviation. So if they ask you to write a representation or a distribution formula, a distribution or formula, if you guys see that, this is what they're talking about. Right, so this word formula right here. Distribution formula, that's what they're referring to. So we wrote that already. Then we're going to label and find the z-score on our curve. Okay. So this is going to be the women's curve. So the 64.5 goes right in the middle. The longer the number is, you kind of want to get slanty so you can fit it. Make the number slanted going down. All right. If the mean is 64.5 and then the standard deviation is 2.5, how am I supposed to find this next number? You add 2.5. You add the standard deviation on. So if I add that on, what would my next data thing right here be? 67. You add 2.5 onto the mean. Then you keep going. Now that we have 67, we're going to add another 2.5. And then add another 2.5 to get your third standard deviation. 72. Right? That's going above the mean. How do we go below the mean? You would subtract 2.5. 62. Alright, keep going. Alright, so we've labeled our curve for this distribution. Let's do the same thing over here. Alright, what's the mean? Okay, standard deviation is the same, still 2.5. So I'm also going to be adding 2.5 and then subtracting 2.5. So if I add 2.5, okay, 74. And alright, make sure you guys are labeling with me. And then if I start subtracting to go below the mean, okay. Okay. Now that we've labeled the picture, what I want you guys to do, and it's all going to be different, because I'm sure everybody has a different height. What? Oh, I don't know. Alright, what I want you guys to do is think about your heights in terms of inches. We did this already, remember when we collected our data? I want you guys to think about your height in terms of inches. I want you in this space to find your z-score and then graph it. If you're a girl, you'd be over here. If you're a guy, you'd be over here. So, for instance, let's do Drew, since you're so confident today. What's your height? Alright, so using the z-score formula, I have the data point minus the mean divided by what? 2.5. The standard deviation is 2.5 in this situation. So I want you guys, or Drew, what would that be? What would your z-score be? Which is 0. So where would your z-score be? It would be right here. You draw a little line and then label it with a z. That's how you find and label your z-score. So when Drew found his z-score, it was a 0. So the 0 z-score is right here. 0 standard deviations away from the mean, so it would be right here, so you would mark your z-score like that. 0.8. Then you would be over here, you just go slightly over, approximate where 0.8 is. Well, actually 0.8 is really close to 1, so it'd probably be like right there. Yeah. So you're just going to find your z-score, and then you have like 1, 2, 3, you're just going to draw a little mark closest to where your z-score would be. Make sure you're putting it on the correct curve. Right, does that make sense? You guys need to know how to label a z-score. So I'm just going to make one up. What if we had a data point and we did our formula for z-score and I got 1.2 as my z-score? How would I label that? You go to 1 and then you go slightly off, slightly above that to mark 1.2. You just approximate where it should be. So you go to the first mark and then slightly over to get to 1.2. So you guys also need to know how to graph a z-score on a bell curve. Does that make sense? You're treating it like a number line. You have 1, 2, 3, and then -1, -2, -3, and you would graph it like on a number line. Okay? Does that make sense? Okay. Now we're going to go into the comparison idea where we can use z-score to compare. So z-scores allow us to translate data from drastically different distributions so that we can compare them on a level playing field. So for instance, I could talk about something that is inches and something that's millimeters or something. Those are very different ways of measuring things, but when you guys turn it into z-score, measurement does not matter. It takes things that are completely different and puts them on the same playing field so you can compare them. So even though one is in inches and one is in millimeters, if you convert it to z-score, there's no difference in how you are analyzing them. This is called, I forget how to spell this, so I need to use this. Sorry. Standardizing. standardizing. There we go. Standardizing. This is where standardized tests come from. They take information from different sorts of tests, from different sorts of students, and they put them on a level playing field so they can compare the scores. That's where standardized tests came from, this idea of z-score. So we get a special normal distribution curve called the standard normal. Standard normal distribution. Distribution curve based on the fact that we're going to be comparing z-scores. So it's important you guys know the difference in how these are labeled. A normal a normal distribution curve is what we've seen before. The one up here, where we had all these weird numbers on the bottom. That's just a normal distribution curve. If you guys are working with a standard normal, you're not going to have numbers, you're going to have these little symbols. You're going to have 1 standard deviation, 2 standard deviations, 3 standard deviations. They're not going to tell you what the standard deviation actually is. They're just going to use a little symbol, right? So when it's a standard normal, they're not going to insert numbers because they're trying to put 2 different sets of information on the same graph. So they're not going to put numbers here, they're just going to have 1 symbol, 2 symbol, 3 symbol, like that. Okay, so it's a little bit different, it's more vague how they label the picture. The mean is represented as a 0. So when you guys are trying to compare data, they just say the mean is 0. We're just going to say, forget what the actual numbers are. We're going to set the mean as 0 on our picture here. The means can be different when you guys are crunching numbers or whatever. But we're going to set the mean to be 0, and that's why we have a 1, 2, 3, -1, -2, -3, instead of the weird numbers we had above there. So basically just trying to simplify it as much as possible so we can compare it. The formula that we talked about before, remember the x squiggle n thingy, right? Instead, this time for the standard normal, it's going to be z squiggle n 0, 1. I'm going to explain that in a second. Z squiggle n 0, 1. So unpacking this one, before we had the x squiggle n, what do you think the z stands for? Z-score. So when you guys are talking about comparing things, you're not going to be talking about the data points, you're going to be talking about the z-scores. So that's why they changed this to a z instead of the x, because now they're saying the z-score is approximately normal when the mean is 0 and the standard deviation is 1. So they changed the perspective. We're not going to be looking at the data points, we're going to be looking at the z-score. So that's why it changed a little bit in notation there. Alright, so we're going to do 3 different examples, just so you guys can see how we can use the standard normal to compare. So I have 2 different sets of data, right? We have the American kind of over here in pounds, and we have the British over here in kilograms, very different units of measure, but we're going to compare them. They're different units of measure, so they're hard to compare, so we're going to turn them into z-scores, okay? So we have a father who weighs this much, and then an uncle who weighs this much. So they're trying to see who is more overweight. We're having an argument or something, I don't know. They're trying to see who is more overweight. Now, if you guys are just looking here, if the mean is 201 and this guy is 225, what's the difference between the mean and his weight? It's 24. And if you look over here, if the mean is 88 and he is 92, what's the difference there? 4. So without using z-score, you would try to say that he's more overweight because that was a 24 and this one's a 4, right? But can you actually say that? No, because this is in terms of pounds and this is kilograms, so you can't make a comparison. 24 pounds compared to 4 kilograms, we don't know what the relationship is there. Okay? So that's why we have to use z-scores. We're not going to compare them on the face value here because they're different units. So what I want you guys to do is draw a little line here. We're going to find the z-score for this dude, and find the z-score for this dude, and then we're going to compare them. Okay? So how do I find the z-score? There's a formula, don't you? So it would be the data point, 225, minus the mean, 201, divided by 23. And you're just going to punch that into your calculator. Let's do the work for you. 1.04. That's this guy's z-score. Okay? Let's go over here and do the same thing for this guy. So what was his data point? 92. So 92 minus the mean, which was 88, divided by the z-score, which was 5.8. Alright, now that we're talking about z-scores, the z-scores are telling us something way more significant than just looking at the difference between the mean and the data point. So what we're going to do is we're going to come over here to the standard normal curve. This guy has a standard deviation of 1.04. How can I graph that on the picture? You're going to go to 1 and then very, very slightly off, pretty much exactly on 1. If you want to just write it on 1, that's fine because it rounds up to the 1 anyway. So this guy's z-score is represented right here. So he is 1 standard deviation away from the mean. Okay? What about this guy? He is slightly below that one. So he is less of a distance away from the mean than the other guy. So if I ask you now, who is more overweight based on this picture here? Who is further away from the mean? The American guy. That's how you guys analyze z-scores, to compare them. If they ask you something about overweight, are you expecting the z-score to be bigger or lower? Bigger. So maybe under this you guys should write bigger z-score. So you guys see overweight, you're thinking, all right, I'm going to find the z-scores. I need to find which one is bigger, which one's further away from the mean. That's going to indicate a higher kind of value. So in our question here, it would be this guy. That was more overweight because he was further away from the mean. Okay. What if I said which one was less overweight? Then it would be the other guy because his z-score was smaller. Right. So think about, am I trying to think of the bigger one or the smaller one? The context clues are in the word problem. Right? Okay, let's give this one a shot. This next one down here. So we're talking about two different people, Mara and Bob. I think we want to turn their heights into inches. Right now they're in terms of feet. So let's go ahead and turn them into inches. So if I had 6 feet, how many inches would that be? 72. I'm going to go ahead and write that down. That's why I left that little space for you guys. And then Bob is 6'4". 76. Alright. I want to know who is taller respective to their peer groups. Now stop for a second. If you guys aren't paying attention to the question and ask you just who's taller, what would you say? Bob, clearly, because he's 76 inches and Mara's only 72. That's not what the question's asking. They're asking, compared to other girls and other guys, is he taller than other guys or is she taller than other girls? That's what they're asking. They're not trying to compare them to each other. They're trying to see who's taller within their peer group, right? So that's why we have to use the z-score. So you guys have to find the z-score for each of them, graph them, and then see which one is bigger because they're talking about taller. So we're looking for the bigger z-score. Okay. Right? So what's Mara's z-score? How would I find it? Okay, and when you do that, what do you get? No, board, don't do it. Is it exactly? Oh, it is exactly 3. Cool. So it's exactly 3. Sorry, my board's acting up. There we go. Right? So Mara's was 3. And Bob, if you do 76, plug in the numbers. What is it? 2.8. Alright, so you can graph it visually or you can just look at these numbers. If they're asking for the person who is taller compared to their peer group, who would you choose? Mara. Because she's 3 standard deviations away from the mean, whereas Bob is only 2.8. Alright, so it kind of goes against, like, if you're just reading the question really quickly and you see just who's taller, you would say Bob, right? But that's not what they're asking. They're talking about, is she a taller girl or is he a taller guy? That's what the question's asking. So make sure you guys are really, really careful to understand that language in the question. Alright, I'm going to let you guys try this last one on your own. We have 2... okay, so we're comparing tomatoes and oranges. Okay? So we're going to have to definitely use z-scores to see how they can be compared. So go ahead and give that a shot. See if you can figure it out. Show me your work. Show me the work for finding the z-scores. And then give some reasoning when you guys decide your answer. tell me how I might find the z-score for the tomato? Oh my goodness. Sorry, say that again? Where did you get the 8.2 and the 2.1 from? Where did you get that information?
Oh, I mean,
It's from the text of the question, right? They gave you the information in the top instead of giving you the kind of breakdown like we had before. It's kind of buried into the word problem, so make sure you're reading carefully. What is the z-score for Mario? Come on, guys, what's the z-score? 1.95. Okay. What about over here? The orange.
It's 0.9.
Orange? Yeah, orange. So what would the formula look like? Minus 10.7. Okay, and then what would the actual value be? 0.94. So if you guys are looking at the standard normal, this guy has almost 2, and this guy has just under 1. So if I asked you who has the smaller groups, it would be the smaller z-score, right? So it would be, yeah, it would be the orange. Right? So that's how you guys compare data. If you guys are looking at 2 sets of data and trying to compare them, you use the standard normal, which is a curve that doesn't have any fancy numbers. It's just 0, 1, 2, 3, and -1, -2, -3. When you guys only have 1 set of data, like we saw at the start of the notes, that's when you guys actually write the numbers in for the mean, the standard deviations, adding, subtracting, and going like that. So you have to understand the context of the question to know how to label the picture. Alright? So in your guys' homework, I want you guys to turn to the homework so I can clarify it for you. The homework has a bunch of questions where you guys are using the z-score formula to either find x, the mean, the standard deviation, or the z-score itself. So you have to figure out what variable you're looking for, plug in what you do know, solve for what you don't know. And then for each of the curves along the side, I do want you to label it. So you have to tell me what the mean is in the middle, and then once you have the standard deviation, you're going to add it on and then subtract it, just like you were doing in the first part of the notes. I couldn't fit that on the answer key because it would take way too much space. So you guys are just responsible for remembering to label the curves using the mean and standard deviation. And then on the other side, there are a couple of comparison questions. Okay? Does that make sense? On the homework? Okay. Does anybody have any questions that I can help you with? No? Everybody's okay? Alright, so you guys can start working on the homework, or you can work on the graded assignment, whatever you guys would prefer to do. But I would like you to be productive for at least 15 minutes.
Can we do the rest one?
Yes.